Hello. Today I'd like to share the results of a predictive analytics project determining credit risk in an accurate, scalable, and ethical manner. As a high-level overview, this scenario involves using a predictive analytic model to improve a business outcome. And 5 years ago, that would have been the entirety of the project. But at this point in 2019, data science has to go a few steps further than a simple accurate prediction. Now, because of the complexity of modern enterprise data systems and architectures, efficiencies in predictive models have to reduce the burden on IT infrastructure, and they can bring benefit to an organization that reaches beyond just a return on investment calculation. Accurate models that can run in real time and provide immediate results also allow for much faster decision making. And as data scientists, we also have to acknowledge that predictive models should be fair. And by fair, I'm not talking about mathematically fair, which really just means mathematically valid. Since the concept of fairness is a cultural and societal one, it doesn't really have anything to do with whether the data is accurately represented in the model. So the best definition of a fair model that I've been able to discern is predicting results based on actions and not identity. So decisions shouldn't be made on how likely some demographic or other is to perform or not perform a certain behavior, but rather on how individuals have behaved in the past. So the background for this scenario is to imagine you're leading a data analysis project for a financial services company, and due to the 2008 recession, the Dodd-Frank Act, and any of the other associated regulatory revisions, your company is revising its credit risk model. So this model essentially runs in real time, and it predicts whether an applicant poses a significant risk of defaulting on a loan if approved. And some of these loans are for, new car, used car, education, small business, retraining, personal loan, that sort of things. It's a general blanket term of consumer loan. So in this scenario, the stakeholders of the project are going to be the consumer lending product line managers. So the business is actually managing and looking for a better return on investment. Of course, it's also going to involve the IT development and infrastructure team because they're going to be deploying the model and maintaining it. And also the legal and compliance teams to make sure that consumer protections are in place and that the model is functioning in a manner that's not going to trigger any regulatory oversight. And of course, the data science team that's primarily going to be responsible for developing the model. Now, the primary success metric for this project is, does this model improve the risk detection performance and therefore generate a return on investment? So is this model accurate? Does it accurately classify applicants as risky or not risky? Secondary outcomes would be, is it fast enough to use in a real-time deployment? So, as the application process is going and as the data is input, it calculates an applicant's risk score and either approves or denies the application immediately. And then also, does the model use appropriate data sources, and is it set up correctly to avoid discriminatory lending practices, which is a big issue that we're seeing more and more as more and more oversight and frankly consumer awareness comes into the predictive analytics space. So as I mentioned in the introduction, at this point, our society is growing distrustful of the power wielded by the so-called big tech companies, especially those with predictive analytics. So anything with targeting and user data and misuse of user data, it's caused the GDPR regulations in the EU and backlash against Google and Facebook is probably the two primary examples. Consumers are becoming more aware that many of the major events in their lives are being shaped in some way by algorithms that they don't understand, don't have access to, that are so-called, in a black box, either because of, intellectual property protections on the algorithm, or because it's something like a neural network where you can look at the data and you have no idea how it actually arrives at that conclusion because, unless you can reverse engineer the loading factors and the gradient descent, you can't actually come to how the algorithm made its decision. And in many ways, this is sort of a cycle of history that's repeating itself, right? So power and insight gradually becomes democratized towards the individual level, usually driven by popular demand and scientific breakthroughs that allow this to happen. So like the printing press and the internet are two great examples of information kind of flowing from, a separated elite down to average consumers and average individuals. And those are very much concerned with the raw data, what is the content? But I believe this new democratization of information is going to be the discoveries and the insights about the data itself. So it's not just what is the data telling us at face value, but what can it tell us in aggregate, and what can it tell us as a predictive tool? So, and as data scientists, our responsibility is to be at the forefront of this trend and act in a way that couples the high impact of predictive analytics with an equally high level of transparency around the algorithms and the source data. So as you see in the little infographic, we have high transparency of process and low transparency of process. So how well do you understand how you got the outcome based on the inputs that you did? And then that's sort of balanced against high impact and low impact or consequences. So for example, a baking recipe has low impact or consequences because the worst that can happen is your cookies don't turn out. But you understand all the steps in the process that got you there. And sort of higher impact version is a jury trial. For example, all the evidence is laid out. It's presented in a well thought out manner. There are lots of controls on how the process is arrived at. But the consequences are considerably higher. On the other side of the spectrum, you have your keyboard autocorrect. Most people don't really understand how it chooses the next word, but it doesn't really matter if it picks it wrong. It's actually kind of funny. There are memes and everything. So there's low impact and consequences there. But when you go up the scale to predictive analytics, it's the same underlying process. It's still predicting the next action, but the consequences are much higher. And so that's a very dangerous space because there's not a lot of awareness of how these decisions are made, but they're very important decisions that are being made. So the first step in completing this project is just to run a pilot solution. So it's a minimum viable product in Agile speak. It's basically a proof of concept to see even if the primary goal can be achieved. Right? So I read the data into R and developed a basic logistic regression model that calculates the odds of an applicant being classified as risky or not risky. And if the odds are over 50% for risky, for example, then that was the risk score applied to that row in the data set. So this used every variable in the data set, which was very problematic for some reasons I'll explain later. But since this is a proof of concept and it's not going to be deployed, it was allowable. So the only step used in data preparation beyond like cleaning the NA values and the outliers was to ensure that the data was properly labeled as a factor or integer, and to coerce the data frame using one-hot encoding into a form better suited for modeling. So I'll explain about that later. But in the end, the data set used was 1,000 observations of 47 variables, which is a comparatively small data set by most standards. So when we look at the pilot model results, we get about 80% accuracy, which is pretty good. And if you look at the receiver operator characteristic chart, you see it peaks pretty early in terms of distance from the random guess line. So this model is showing a benefit quite quickly in classifying these observations. I also ran a naive Bayes algorithm and a random forest algorithm on the same data to compare the speed and the accuracy of the different model types. And the random forest ended up being slightly more accurate, but significantly slower to train and calculate. So much so that I ended up just disqualifying it from production, because if it's going to take that long on a relatively small data set, and we're not talking a lot of time, we're talking about a second and a half, but this is a small data set, and at any time it would be brought onto a server, the computational complexity is going to increase by an order of magnitude at least, and it's just going to be too slow to operate. The naive Bayes algorithm did show a lot of promise, though, in terms of execution speed, and and a couple of other factors that I'll explain later. But that one was also showing a dramatic increase. So at the end of the day, the pilot project showed that yes, the primary goal is feasible. The ROI is actually pretty significant, with a positive returns occurring in the first month. So we see a positive $61,000 ROI in the first month, and that's from an increase in accuracy between, instead of 70%, which is basically just assuming that every applicant is no risk and being wrong 30% of the time to only being wrong 21% of the time and being right, that it reads 80, it should be 79.5% and 20.5%. So it rounds up. But it actually drives a pretty good increase in the expected value per loan. And when we apply that against 100 loans per month as a run rate, you actually get pretty good profitability. So as a proof of concept, the pilot is solid. So that takes us to the plan for modifying the pilot to actually come up with an implementation solution. So now that we know that the positive return is feasible, we have to maintain the efficiency we saw with calculation time and maintain the accuracy, all while using less data, and that is like fewer variables. We're not using fewer observations, but because some of the variables are problematic, we're going to exclude them from the data set and attempt to at least maintain performance. So this involves some expertise because it's frankly much easier to build algorithms that use any and all available variables. The trouble then comes with when you put variables in your model that act in such a way as to influence the outcome in a discriminatory manner. So they can reinforce actual discriminatory lending practices because they're included and they're not immediately obvious that they're, in some cases, they're not immediately obvious. In this case, they are immediately obvious that they're problematic variables. But yeah, they can really cause a very bad outcome if they were actually put into production in terms of a effect on human society. So to overcome these challenges, I switched to using a naive Bayes algorithm to classify the observations. Now, naive Bayes algorithms use Bayes' rule to calculate the conditional probability of a dependent variable taking on a given value. So in this case, 1 indicating a default risk, given the values of the independent variables for that observation. So for example, if you have a data set about animal characteristics, right, and you're going to try to classify each observation as, is it a dog or is it a fish? The naive Bayes algorithm would calculate the probability that a given animal is a dog or a fish given the values in the data. So if the data indicates that an animal swims, that might not provide a lot of information since dogs and fish both swim. But if the data said that the animal had scales, that would increase the probability that you're looking at a fish, for example. I mean, very, very low probability that an animal that swims and has scales is in fact a dog. So the naive Bayes is very, very popular with real-time IT solutions. For example, your email spam filters use it, Google search results use it, the autocorrect on your phone's keyboard uses it because it runs very, very fast on very small data sets, because it's essentially the processor in the background is really just doing long division and multiplication. It's not trying to match a gradient descent formula or optimize a least squares measurement. The big issue affecting its accuracy, though, is ensuring that the naive Bayes is actually, in fact, naive. That is, that the variables are independent of each other. So going back to our animal example, the likelihood that an animal swims, for example, shouldn't change the likelihood that it has scales, or at least it should change it very little. Right? There shouldn't be too strong of a correlation. Now, if that condition of independence can be found in the data or built through a statistic transformation or cleaning process, the naive Bayes becomes a very good choice for this project. As far as the project actually developing and implementing the model, this pseudo-agile chart showcases the responsibilities by major stakeholder group, along with a timeline of events. Now, it's not explicitly called out, but sort of implied along with the agile methodology is that this work is actually divided into 2-week sprints, you can see in each iteration, in which each team accomplishes a defined set task, and after that, the next iteration is developed based on the findings and results from a previous iteration. So this is very much a living document, and it can and should change as needed depending on the evolution of the project. So each iteration builds upon each other, and one of the cornerstones is that each team has regular communication and collaboration meetings called sprint meetings. They also have sync meetings, sometimes on a daily basis. In that case, it would be called a stand-up meeting, where representatives from each of the stakeholder teams actually collaborate in a room and say, here's our progress on this task, here are our obstacles, here are our findings, there are no impediments that we have to executing this task. And so in that way, every member of every team, or at least every team's representative, is kept appraised of the progress that every other team is making. So it's a really, really great way to collaborate through cross-functional teams that may or may not have a lot of visibility normally into what each other are doing working toward a project. But this sort of ensures that everybody knows what page they're all on. And it's also a very dynamic process, so you don't organize the project, top down, start to finish. You set up sprints with proposed tasks, and then they definitely do change as the project evolves. And that's sort of understood and baked into the methodology that that's okay for goals to change and for tasks to change, because we understand that you don't know what you don't know going into it. So in terms of operational concerns, there are definitely areas where special care needs to be taken and issues preemptively addressed. So these are called out, and they'll kind of relate to the project's goals. So implied along with the previously stated goals are the important points here on data security and data integrity. So anytime consumer data is stored or transmitted or recorded or used in any way, there should be really strict controls around encryption, safe storage, so not storing personally identifiable information and financial information on the same database, and controlling access to any joins that would occur on those databases, anonymizing the data if possible. And if you're looking for trends, you can use anonymous data. It's not really an impediment. It's only when you're trying to match the performance to the demographic data, but we already discussed how modeling with demographic variables is not a great idea from an ethical standpoint. So really, anonymization is actually a really good way to go. And there should also be access controls. So, we have a well-defined project team. So members of the project team should be granted access to the data on an as-needed basis. It shouldn't be something that's just sitting on a server somewhere where anybody with the right credentials and some curiosity can peek in and get access to that data. And I think now in 2019, we're seeing that companies are learning this as breach after breach happens. They're starting to learn the consequences of sloppy data protection. So moving back to the algorithm and to the modeling aspects, the key to making this algorithm work is the proper preparation of the data. So in this case, there were immediately problems with the variables, namely that kind of amazingly, female applicants didn't seem to be represented at all in the data set. So that your choices for marital status, for one, would be male divorced, male single, male married or widowed, and that was it. So I'm not sure what year this data was taken from, but it's definitely not appropriate in 2019 to have those variables in. It's never appropriate, but I think now there's a very clear understanding of the consequences of modeling using those variables. Age was also included, which is extremely problematic, as is the field that indicates if an applicant was a foreign worker. I'm not entirely, I'm assuming that means someone on a work visa. Also not a great variable to model on. So yeah, if a model was built on those variables, it would almost assuredly result in discriminatory lending practices. So those were stricken from the data set from the outset. Now, to ensure conditional independence among the independent variables, I used Goodman and Kruskal's tau measurement to measure correlation. So this data set was actually really challenging because most of the variables were encoded as factors. Instead of numerical data or even ordinal data, they were categorical data. So a numerical correlation wouldn't work here. So instead, Goodman and Kruskal's tau was used because it does work well with categorical data. And it's also asymmetrical, which is a really, really important point for data science, because what it means is that instead of like a chi-squared test or a Kramer's V test, which gives you one value for the correlation, it reflects that correlation differs based on what you know. So as an example, if we go back to our animal example, if we know, if we're trying to predict whether an animal is a fish or a dog, right? And we have two variables, right? Gills or swims. If we know an animal has gills, it's probably pretty highly correlated that it swims, right? We can pretty much assume if it's got gills, it's going in the water so it can swim. But conversely, like if we know an animal can swim, that doesn't really tell us if an animal has gills or not, and not with as much certainty, because a lot of animals can swim, may or may not have gills. So the details of the transformation are in a technical handout that I have, but essentially the GK tau is calculated for each combination of variables, and any of the variables with a combined score over a certain threshold were removed from the data set because they were just deemed as too correlated. And finally, the data is coerced using one-hot encoding, which takes a categorical variable, for example, with two outcomes, and actually makes it two variables, each with a yes or no response. So instead of a variable indicating, like if an animal has gills or lungs, like breathing type would be the variable, and gills or lungs would be the possible choices, the variable is actually split into two variables with a yes/no response. So one variable is, does it have gills, yes or no? A second variable is, does it have lungs, yes or no? So this type of transformation gives a much cleaner read for most predictive models when you're using categorical data, since new variables can be de-weighted based on the response without really affecting the other variables. So if you have unrepresentative data sets, or unbalanced data sets, that is, where maybe you have one of the values in a variable is much less represented. Maybe you have two animals with gills and 4,000 with lungs, right? You don't want to de-weight the whole variable as not important, but instead you can look at it as, when you split it into two, you can actually see the importance of each one independently. So it's actually a really good sort of best practice for any sort of classification data. So now the result of the transformation, the implementation of the naive Bayes algorithm was actually very positive. So the accuracy was increased to 82%, with an area under the curve of 76% instead of the 73% we saw in the logistic regression. So again, just as a reference, 50% area under the curve is what you get from random chance, and 100% is perfect accuracy. So both models are fairly strong, but the naive Bayes definitely did pull ahead in a significant way, while using less data and, as we'll see in the next slide, calculating at a much faster rate. And the credit is not necessarily the algorithm, but matching the data preparation to the algorithm. That's a very key point, because you are using less data and it is more difficult to get a good, solid, accurate read. But if you match the algorithm and the preparation and you do your due diligence, you can get a very strong result. So when we run the ROI calculations, that 2.5% increase in accuracy nets out a first month incremental ROI of $42,000 over and above the pilot implementation. So that's a 69% improvement in ROI for month one. That's a big increase, and just bottom line revenue. And the algorithm ran almost 20 times faster than logistic regression. Again, because we're setting it up for the most efficient execution possible. So in the end, this project, after careful data transformation, algorithm selection, it does meet all the project requirements. So it runs very quickly, providing a good user experience for a real-time decision on credit risk for a loan. It uses data built on applicant actions and not demographics or identity variables. And it does also provide a significant return on investment for the business. So the implications of this project are more significant than I initially thought they would be. It demonstrates the so-called law of small numbers. I believe that was originally a term coined by Levitt and Dubner in their book Freakonomics. It states it's sort of a play on the law of large numbers, right? Which relates to the central limit theorem, where if you have enough data, they'll start to converge on a mean pretty quickly, and you can see trends over the long term. And, that's definitely true. But when we look at like small increases over time do also add up to significant results. So if your algorithm can be 2.5% better, you can get a 69% improvement in ROI. That sort of scale is huge. It's one of the key strengths of predictive analytics is you're not trying to predict with 100% accuracy. You're trying to tilt the dice just a little bit more on their way down. And at the end of the day, or at the end of the year, the fiscal quarter, you're going to have a much, much higher return on your investment just because of that increase in accuracy. It also highlights the challenges in predictive analytics that can be overcome without resorting to including problematic variables or modeling in an ethically questionable way. It's very tempting to lean on the algorithm and lean on the model and say, well, the model needs this, or the algorithm needs this, or the data is included, so why can't I use it because it's there and it was volunteered? And that really gets down to the ethics of it. Like, are you trying to move fast and break things, or are you trying to provide benefit? And data science is, I believe personally, is about solving problems and challenges that we can't do other ways. And part of those problems shouldn't just be math problems, right? They should be human problems. They should be solving things in a way that drives benefit to everyone and finds a win-win scenario, because with powerful algorithms and vast amounts of data, win-win scenarios are very, very possible. And it really falls on the shoulders of the data scientist to find the statistical methods and the techniques that will work given the constraints of the scenario, rather than falling back on the safer and easier strategy. So in terms of future developments, this technique or others similar like it can be used anytime a data set has to be truncated for ethical reasons and accurate calculations have to be made quickly. So any industry where you want to provide human dignity, I guess is probably the best way to say it, is anytime you want to, you're not just looking for a return on investment, but the decisions of the business have human consequences over and above, a simple change in the numbers. This is a really good technique to use because you don't actually need a lot of data. I mean, this is done off 1,000 rows, and I think the final count of variables was something like 20, which is not a very large data set, but it can actually provide a significant findings. Anytime it has to be truncated in any sort of industry where we have things like insurance decisions for coverage, healthcare coverage, healthcare readmissions for hospitals, finance, like we've seen, credit loans, foreclosures even, any industry that has dealt with historically discriminatory practices, right? Anytime there were ethically questionable decisions made in terms of, discrimination for any reason whatsoever, this can provide an action because it's only using data on what an applicant or person or subject or observation does, not who they are, not any sort of underlying identity variables about that individual. It's really based on their actions. And so it's a very, very powerful tool to use. And it really comes down to matching the statistical transformation of the data and understanding how best to fit it to the algorithm and selecting the best algorithm to meet your needs, rather than simply, plugging it into a black box neural net and throwing up your hands in the air and shrugging and saying, well, that's what the data tells us, so it must be fair and we should all listen to the model. That's not data science. So thank you for your time. I hope it was informative. The technical details are available in the technical handout. And if you have any questions, please feel free to reach out to me via email. Thank you again.